Hello everyone, welcome to the graduate student community at Gallery College of Engineering seminar series. Today we are excited to have Dr. Ramani, Professor of Mechanical, Electrical, and Computer Engineering at Purdue University. Before we begin the talk, I would like to introduce the GSC leadership team. First, let me introduce our leadership team for this semester, including our co-chairs, Rodney and Samuel, our publicity team, Avinash, Hafiz, and Subnil, our co-treasurers, Anshu and me, and our support team, Zarin, Roshan, Rachel, Suramia, Vipa, and Nurain, and for sure our mentor, Professor Farah Misri. If you are interested in learning more or joining the leadership team, please feel free to reach out to any of us. Every week, we have leadership meetings on Wednesdays at 6 p.m. on Zoom. If you would like to join, please email Rodney or Samuel, and they will provide the Zoom link to you. And also, the meeting times may change each semester based on the students' availability, so you can share your availability as well. As a quick reminder, if you have not already joined us, please become a member of the GSC on Engage page. Your membership helps us secure funding for seminars, other events, and of course, providing launches for these seminars for this semester or the next semester. Also, please follow us on GNC LinkedIn page to stay updated on future seminars and events. For each of the seminar, we post in advance the information that are needed to join our seminars. We also encourage you to connect with us on Facebook and Instagram. We use these social medias to share seminars, invitations, updates, and opportunities to stay connected with past and present members. Also, past seminar recordings are available on our YouTube channel. So if you ever miss a session or want to review a talk, you can easily find it in our YouTube channel. If you would like to join the GSC leadership team, you will have access to the Bird Team Room, which is a perfect workspace with couches, whiteboards, a coffee machine, and a microwave, so you can study or collaborate with other students anytime you want. Also, please fill out the seminar attendance form. The link will be shared with you in a chat box. This helps us track participation and secure funding for future events. For this semester, we are focusing on exploring research frontiers with generative AI. We seek to feature speakers who can address one or more of the following topics. First, how people can work with generative AI to create intellectual, economic, and social value and connect these domains. Second topic is research issues, methods, and applications that arise when people collaborate across research, industry, and community. And the third one, ways to design generative initiatives that link academic inquiry, economic innovation, and social benefit in ethical and equitable ways. So if you or anyone you may know works in this area, please let us know your nominees and they will be our next speakers. Also, we have 3 upcoming webinars highlighting human-centered, ethical, and somehow collaborative AI. We will have Rohan Doctor will discuss using AI to connect people. Then Rustam Kanga will focus on ethics in AI. And also Vishnu Kadiwala will present research on multi-agent coordination. And now I am pleased to introduce our speaker, Dr. Ramani, with today's talk on physical AI for human-centered perception and action. Now I will stop sharing my screen and pass it to Dr. Ramani. Thank you, Dr. Ramani.
Yeah, thank you so much for your nice introduction. Okay, is the screen clear?
Yes, go ahead.
This is Yes, clear. Dr. Rahman. Yes.
Great. Okay. So yeah, thanks. Thanks to Farouk for having invited me. Little bit of an accident. I got a link, and it was from Farouk. I was doing some work, and normally I don't get a Zoom link from Farouk. So I got in, and of course, it reminded both of us that we exist, and here I am. So thanks, Farouk, for inviting me. So today's presentation, coincidentally, of course, I've been working on this AI space in particular since around 2010. So I'll kind of little bit of that thread, the history thread will be there, but also moving into forms of AI that are emerging or emergent, right? So you'll see a living thread from those times pre early deep learning days all the way to the new AI, both in Gen AI form and LLM forms, and so on and so forth. But first, I want to sort of talk about very quickly some transition that we have seen in the community itself and in general from the so-called information age to age of what I kind of currently call it. I call it age of physical intelligence or embodied intelligence, right? So of course, in the beginning, we miniaturized electronics and the shrinking of computers from very large sizes, right? Like the size of the Volkswagen there, and even bigger when I started computing, to extremely small miniature forms of being able to compute microprocessors, sensors, MEMS device, and then we connected everything, the so-called IoT age. And we built, of course, tools for been building such tools for design and simulation and analysis and optimization and so on and so forth. Multitude of such tools. They got commoditized, of course, and accessible and available everywhere. Same happened with machine tools also. The center of gravity moved away from us since the early 90s to now. So we kind of globalized a lot of these things. But with that, all of a sudden, more recently, we started seeing the explosion of new ways of reasoning with language. And language is very important. Of course, we think and write and do a lot of things with language. So AI being able to do seemingly nice things with language and then give rise to so-called visual language models and so on and so forth, an ability to do very tough problems, Olympiad level math problems, and also write code, perhaps at beginner intermediate level, help develop a lot of those things. So we are sort of seeing a reinterest in robotics and humanoids and so on and so forth. So a lot of this sudden change actually happened because of a couple of events historically. So I'll kind of identify those and then move to the main theme of my talk. So the opportunities going into the physical side of AI is an opportunity for all of you, right? And fundamentally, a lot of these AI problems deep down are areas of expertise of Farouk. They're all basically set up like optimization problems, right? Like, so if you're good at optimization and setting up these kinds of problems, understand constraints, etc., the basic idea should not be a problem. But of course, the mechanics of how things happen, there's a lot of stuff going on there and has been going on. So two important events, if you look at history of AI, 1943 to now, I'm not going to get into all details, but one of the first ones was the so-called deep learning networks happened around 2011, Nature paper, Jan LeCun, Jeff Hinton. Jeff Hinton actually recently won the Nobel Prize. Curiously, 2008, during similar sabbatical to one that I took, I was both at Stanford in computer science, but prior to that, I was at UCLA. And at that time, I interacted with Jan LeCun. At that time, he had only 1,500 to two, I mean, very, very low number of citations. Of course, now he's Fields Medal winner and very famous. So my interest kind of got triggered during that time in 2012, and I continued my work in that area using our core in geometry. So next big thing happened in 2017, which I want to kind of point out, but won't get into details. It kind of, a lot of my talk touches upon transformers. Transformers came out in a 2017 NIPS paper, as I just saw recently today, 238,000 citations since then. And pretty much a lot of the Gen AI is built on some form of transformer architecture, pretty fundamental to it. And of course, the team, Ashish Vaswani and others, didn't realize that when it scaled, it can do even more interesting and have huge impact on many things, right, around the world. And that happened with the commercialization efforts of ChatGPT and so on and so forth. So quickly moving into physical AI. Physical AI, I'm kind of going to broadly just set the context for it. And essentially, the idea here is that, of course, it's embodied, meaning like, in my case, I'm going to be involving humans physically in immersive systems, as well as other situations and contexts that AI can help us do stuff, do work, learn, play, and so on and so forth. But also, if you sort of look at it more broadly, the ideas of physics govern a lot of other settings of AI, which I won't touch upon in this talk, but I'll be talking more about embodied AI. So the mysteries here, early work in this area, of course, started with Claude Shannon, Seymour Papert, both of whom had associations with MIT, computer science and AI labs there. But also we sort of start looking now at human cognition, perhaps even some neuroscience, as well as other situated contexts where the AI kind of can come alive, right? So language and scale, both are not the whole story, but language and scale is what made the change between 2022 to 25, pretty much, right? Like OpenAI, pretty much scaled the data, scaled the compute, scaled the capabilities of what transformers could do. And we saw a lot of amazing things that AI could do. And also, of course, big limitations of the current form of AI. So this very early work by Licklider on man-computer symbiosis, right? It sort of has been an inspiration to a lot of the work that you have been doing, but also looking at the big gaps between what AI can and cannot do, and how we in the engineering area can think about AI in new forms. Some very early work in augmentation, of course, I'm not going to get into it, was all done by Doug Engelbart, 1968, mother of all demos. But he also showed headsets and showed that when you put vision and compute on the human body, and the machine is also seeing what you're seeing, perhaps not the same way, you can do a lot of things. And with it, we sort of have seen the emergence and growth of the so-called extended reality and other forms of reality. And it's kind of a fundamental change in the form of computing. Of course, it comes up and goes down because these devices and the ecosystems haven't yet matured. But in general, the on or forward direction, a lot of the compute and training of robots and so on and so forth are already starting to happen with first person videos, and they are data hungry, showing how humans, excuse me, interact and do things in the physical world. So embodied AI is very a part of the journey here. But in terms of creating these AR, VR, and all this extended reality applications, it takes a lot of expertise of humans, takes a lot of effort, takes a lot of coding, takes a lot of customization. And by the time you're done, you spent a lot of money, and then you get an application which is hard to change and edit, and pretty much, doesn't get used because of a lot of these issues. But if you kind of think about it, right, like YouTube per minute, how many YouTube's videos are created? How many of us learn from YouTube, et cetera, right? It's humongous, right? So for immersive reality to succeed, not only the device and other things should be compatible and socially acceptable, et cetera, but more importantly, you should also be able to create thousands of applications, right? Right from all your labs to many things that we do, maintenance, repair, overall, et cetera, et cetera. Anything we deal with in the physical world, right? Including learning and coaching for athletics, which I'm going to talk about a little bit, right? So, so the idea of embodiment is pretty old. It's not new at all. But where I think the changes have started coming with the new AI is is a lot of it, like position tracking to eye tracking to hand tracking, body tracking, object detection, understanding, scene understanding, etc. A lot of these things have taken new form and capability, right? And and if you kind of think about it, right, like things happening spatially, but also we have a lot of devices, phones and tablets and so on and so forth, right, where there's vision embedded in it. So there's a joint space that all of us share, which is the physical world, and that becomes the playground where the so-called spatial computing, some forms of AI, the human, which we live and work and do things in that area, and many of these emergent technologies can interact with, including robots and humans, as well as anything with embedded Internet of Things kind of capability. So the three parts of the talk in the rest of time, like I was asked to talk for about 50 minutes. I'll probably do so. So it's about 10 now. So I'm going to talk about these three pillars, right? First pillar is very focused on understanding. By understanding, what do I mean? I basically mean human perception, human language, and the context, right? Or what are you doing? Where are you, etc. Things surrounding you and your local ecosystem that you care about in that situated context, right? So we'll talk a little bit about that first. Then I'll move on to authoring, and then I'll move on to interacting, all in a more spatial form. I will sort of bring CAD and design, right? Like the so-called CAD, computer design. I'll kind of turn it upside down into design aided by computers, sort of show how we can do a lot of operations to create 3D CAD just by talking and showing things with the hand, right? So I'll show that towards the later part. In fact, large part of my class that I developed and used, we are seeing that we can start using these new forms of compute to do a lot of the design, just geometry in that case. So the future of augmentation will touch upon that, but sort of like a cartoon framing for the rest of the talk, right? What do I mean by understanding and authoring? But basically, the idea is like, let's say you're doing something in a video, right? See it in a video, which is one very common big form of media that we can use. And in this, we can attempt to estimate human pose, which is pretty much a well done problem. Action recognition, on the other hand, has continued to be of importance, and it continues to be of importance even now. And with the emergent idea of like, let's understand what people do in the physical world, and can the AI learn from it? Can the robots learn from it? Because of that, this has become very critical. So not just the video, but also what are you doing? How are you doing? Getting multimodal data to annotate a first-person video, which is simply like a camera put, let's say, on your head, looking at what you're doing. All those kinds of content have become extremely critical now. So, for example, from this, we can say textually a person is assembling a furniture, right? The reverse of it is generation, right? So if I say a person is assembling a furniture, right, in textual form, can I generate the human pose and the human actions, and the humans actually assemble the IKEA furniture? In fact, there's a fairly big data set which is pretty popular, the IKEA data set, right? Like for assembly purposes and so on. And then this can then come alive in spatial, which is like in augmented reality, right? Augmented reality as opposed to virtual reality. AR happens in the physical world. VR just happens in your headset, right? It doesn't have to be real. So AR, of course, is of much, much, much more greater economic value than VR alone. So now kind of three things perhaps you can take away from here, right? Embodied authoring, right? Can we teach machines by showing and or talking, not coding? That's one piece. Second piece is like shown in multiple, I mean, all of these, there are fairly large number of papers and students that have worked in it, perhaps more than uh, uh, 20 or 25 PhD students since 2010. I lost count there, but I'll give you some very interesting examples picked from those, right? Ghost AR, Agent AR, and Caring AI. These are three things which show embodied generation of either humans, and in later case, just shape, which I'll show, even designs, right? By using verbal textual alignment with things that you show. Then an interesting twist to this is what happens when AI can see, it can sketch, and can it build with us, right? And then finally, I'll sort of end with embodied learning and skill augmentation, sort of transferring our skills and doing stuff. And I'll use table tennis as an example, in particular, because I know the sport very well and understand the physics intuitively well, to see how we can create avatars that can coach people, but also can we transfer our skills in table tennis to humanoids. And we just had a paper accepted in ICRA just a couple of weeks ago to show full body control of a humanoid, of a real humanoid. Collaboration work with a colleague of mine, Yan Gu, to for it to play very basic table tennis, right? Like I'll get to that in a later part. But roughly speaking, one of the important things that sort of took me a while to actually formalize in this slide is that spatial compute, 3D, where the human is embedded, is not 2D plus 1D. There are a lot of hidden dimensions and complexity, right? Which gives rise to entire new field, and thousands of people are working in computer science, in ECE, and in some cases mechanical as well. I mean, really, it has no boundaries in that sense, right? Like to discover how this can be done well, and sort of go beyond a lot of things that we think about, like human in the loop or easy to use and intuitive. What do these really mean, right? So one of our very early works, actually, this was work done by one of our very early students who was taken into our group on recommendation of Professor Misri, Ayan Sinha. He was one of the early persons worked in this area. But basically, the idea here was inspiration from recommender systems. As you know, like recommender systems have been used extensively in places like Netflix and all the things that you do on Amazon when it's coming up with suggestions, ads, and so on and so forth. If you did this, it perceives from a lot of the actions that you have taken in flat computer systems and says, "Oh, you did this. Do you like this?" or and so on and so forth. So we kind of got inspired by that idea because that was very nice system to start build upon. So kind of think about it as analogous to a recommender system, right? So the idea here is that we estimate a hand pose in this case because hands are extremely critical for AR and VR. It's the foundation by which we interact with stuff, right? And literally the whole world is scaled upon and built upon what we do with our hands, from pens to pencils to computers to keyboards to rooms to buildings to cars, etc., etc. It scales in some human-like scale manner. So hands are important. So can we estimate the pose of the hands very quickly, right? So we take a image of a hand and we kind of create let's think of a fingerprint of it. It's some kind of a pose using some kind of a feature vector. And then what we want to do is find similar hand poses in very large data set. Let's say we have a data set of manifold of all hand poses, right? It's kind of finding users with similar tastes in movies, right? Like this recommender system idea nicely can reduce your search space. And then we can impute the hand by local interpolation once you get nearest neighbors, for example, right? So this kind of an idea actually turns out worked pretty well. It was one of our very early papers. And since we have had numerous publications in the hands area, all the way from WIST 2012, where we showed two hands, all fingers touch on a table, making a table into a drawing board with a single camera, to more recent ones. So very quickly, I'm just going to show you a little bit of this piece of work. Again, like I said, very early work, but you can see even in those days, and this is like history for this area, we are dynamically able to reproduce the motion of the hand, which means the AI in some ways, in this case, the deep neural network has learned the constraints of the hands. That was very surprising, right? A lot of the biomechanical constraints and so on and so forth. Perhaps the hand says 28 degrees of freedom. And this is a long-standing problem in CS. Now with objects and occlusions has become even more important, right? So I won't get very much into this algorithm, but basically the idea is is to use and leverage a deep learning network, but also kind of guide it by the structure of the hand, right? Like, so we do need structural priors to guide these AIs. That's something that we learned pretty early on, which continues to be one of the mainstays, even in the most recent work I heard yesterday from Likun or Jitendra Malik, some of the big giants in this area, they all continue to use structural priors, right? So, and then like wrist rotation, et cetera, all these can be regressed, and you can actually impute the hand features and get the unknown parameters. So basically, you're fitting. Think of it as a fitting the hand in a dynamic manner. In that case, we were doing it at like 30 frames per second, but of course now much better. Like fast forward, this is very recent work, and prior to like just when the attention network started getting everybody's attention, we were working on it even earlier, like in the 2020 timeframe. So what we did was we said, okay, language is pretty good. It can, complete sentences, do much more these days with AI. You can even sort of almost write a whole paragraph given some intent that you want, right? Like, so that's sort of like filling the blanks kind of a thing. So what we did was we occluded the hand, like put some mass, and then trained it jointly with the language model. So basically, the idea is just like predicting blank words. If you take out some of the hand geometry which is not seen or body itself, we did it for the whole body. Can the machine be able to predict the occluded joints and sort of like build the semantic connectivity between the joints in a very general manner, right? So it turns out that you can, again, this we kind of made it work, right? Like in a lot of these things, the trick is trying to come up with a representation and build an architecture which can do this, right? So the objective of this masked joint modeling was to reconstruct the masked joints given the visible joints, right? So it's one of our work. And sort of continuing on that, this is sort of more an HCI implication of the work. So in this case, you're seeing like hands, both discrete gesture, a continuous gesture, and static hand pose and dynamic hand pose, right? So sort of some examples of things that we have shown in our papers, like virtualizing the mug. You can do this very easily with Gaussian splats these days, even in a dynamic manner. And here, a Coke can, right? Like here, dynamic provoking, like you're just closing the hand and then like the cup bursts. So a lot of these, and here giving it actual behavior like a spring, right? Turns out a lot of these things are hard to author. So we kind of made these things possible for people to author I just excerpted this out of a paper. So I'm not going to get into some of the theory here. This is one of our fairly highly cited papers in representational learning. At that time, we did hold the record for action recognition. Of course, this is a fast-moving area, but our idea was not to build a data set and come up with the best action recognition algorithm, although that happened at the time. Our goal was to better understand what humans do in physical world, but we had to build some of the foundations for it. So here, if you look at a human body, right, you can have topology extrinsically, like the bones that connect the points. That's kind of like a naive representation of the body. It turns out that if you want to discriminate among various human actions and not only be able to label it, but also say what the human was doing at that time, you need a representation which is much more discriminative. So here we built some representations which used this idea of self-attention, but also, there was a theory here, but the main idea here was to model the intrinsic topology, right? The connectivity between maybe your palm of your hand and rest of your body when you're doing some particular action with the hand, right? So the intrinsic topology is actually modeled, and these connections are represented using the so-called self-attention graph. These are all latent features. Actually, there's no explicit graph model you can actually draw for it, but basically they are learned features, and we built it. So an example, right? Like you can see the lines between the hand and other parts of the body, and some of these are darker, showing that there's a greater connectivity, greater connection between that part of the body and the hands, and the rest of it are weaker connections. But again, it's learning the extrinsic topology from actions, and it can be used. So I'm going to kind of shift now to show how you can author, which is creating how you can orchestrate between actions of human, maybe a machine, a robot, or whatever, and then like how to take that and do other things. So kind of coming back to like more a mechanical engineering setting here, always we have seen that people need to know how to do things physically. You always ask people, how, can you help me set up the 3D printer? How do I load the material? How do I do this? How do I do that? A lot of these things, right? And typically you go and watch in YouTube videos, but they are static and one way, and like, it's not embodied, right? So we wanted to create a two-way interaction between the human and the avatar here, which can actually show for you how to do things. Of course, you can replace it with a human art, perhaps. And if it had a dexterous hand, maybe it'll even do the tasks. But the hands are far away from reality yet. So in this, we kind of show an avatar showing you, and you do it. So the embodied authoring part of it is simply taking a video of the user, for example, and you show what to do. And also in that process, we developed a model for level of detail for the tutoring elements. I'll show that in a minute. And then in the forward motion, in the forward path, right, we wanted to recognize the user state. And then there's a high level inference, which sort of makes a decision on how the avatar is going to adapt or help you, right? For a particular learning goal in this case. So in this case, like when we did this adapt tutor, that is adaptive embodied tutor, we kind of were showing a lot of fixed cases. This year, we have been able to generalize this kind of stuff across many things in a paper, which is the work was just done and accepted, ARIFI. It generalizes this, very similar to generalized mechanical intelligence. It generalizes authoring from videos more than this. Okay, so adaptive training, like just think of level of details, right? Right? No elements at the top, a subtask description, and then expectation of a sub-step, right? Like a sub-step description, and then like having more detail, animated components and sub-task description, and then like full avatar, right? Etc. So sort of breaking that into different modalities of help, right? Like just a quick example here. Yeah, so sort of trains it on training it on different types of knobs and elements and so on and so forth, right? Like so it understands what you're doing first. Here it's sort of telling you, setup operation. Sorry, I couldn't take the volume out. Anyway, but it sort of is helping you do the particular step and stepping in to help you, right? Like so it's sort of more bidirectional, but also embodied, and it shows the elements right where they belong in 3D, right? Like if you're moving the slider, holding this, doing that, etc., those elements, right? So moving little ahead, right? Like we wanted to also now start capturing the context, like what is it that you're doing, how you're doing, and allow the end users to build customized context-aware programs. That is, you're creating your own program, right? So the idea is like the backend code and all of that is you're not oblivious to it. So it just happens on the back, right? So the augmented reality authoring for such context-aware programs. So how do you browse, select, edit, and make the whole workflow for this very smooth? So it's clearly a visual programming construct. So we, let me see here, a little bit of cap here. Yeah, of course, this was, you can see that we actually hacked into the headsets with the cameras and so on and so forth. But also you're kind of building a lot of what if then kind of metaphors just by connecting, for example, in this case, like there's a medicine bottle here. If I take my medicine today, what time did I take it? Is it the first one or the second one? So they AR should know and decrement the counter, its virtual counter, etc. And then we IoT the coffee maker and a bunch of things around you, the night lamp and so on and so forth. So and the clock, right? A virtual clock in this case, not a real, and a virtual Nest thermometer. So there's virtual and physical stuff going on here. So how do you connect all of these and build logic into it in the physical world using actions? So that's kind of what we demonstrated here. Yeah, this is turning the kettle on, all of those, right? Like, yeah, depending on what you want. So you're the author, you figure out what you want to automate and how you want to automate. You build the logic in. That work was done by Shun. Actually, Ayan was also Farouk's student, is now, I wanted to just mention on the side, director of AI/ML at Upwork. Shun and multiple others, they all work for either Meta or Apple or Google or their startups. So a lot of this work was done by several of our early PhD students. Sort of coming to more recent work, here we sort of wanted to start bringing the text modality to control the avatars, to see whether we can make the avatar do, throw a ball, play, move, right, etc. Not just do one action, but can we smooth between the actions? So that was the idea here is given text, can we create a sequence of actions and do this. This is joint work with Honda Research Institute. Turns out that the compute capabilities and others that you need were much higher. So and also student was an internship, so we just partnered in this project. So can it do all of these, but also together with that, can we make it very versatile, increase the fidelity, increase the smoothness? All those are current issues that we face in human-generated avatars being able to do things realistically, right? So yeah, here again, a little bit of attention kind of network, but also we introduced this idea of a dynamic transition probability. Basically, it adjusts the motion tokens and so on and so forth that are generated in different environments, different form of sampling, and it sort of introduces this idea of a discrete diffusion model and makes the motion smooth. For example, in the right hand one versus the left hand one, right? Person walking, petting a dog, and then walking normally in a circle, moving the legs and moving forward slowly, right? So the idea was to get more smooth motion across different tasks, so multiple different tasks. Sort of fast forward, we used that M to D to M and did something in this one that was more a foundational contribution. But here we instruct the avatar to actually do things in a physical space with physical things. So there are multiple moving elements to it. I'll just break it down and sort of tell you quickly. But basically, codeless motion capture free workflow, right? There's no motion capture and so on and so forth, which was the hallmark of old forms of computer graphics and avatar generation and so on and so forth. But also now we bring the idea of using actual real world examples with physical objects and virtualize the physical objects sort of in situ. So generative AI that is contextually aware of the human, of the environment, and the system. So pick a PVA filament, go to the printer, attach the filament to the printer, start the printer, right? We can start getting into details of can it actually start operating the printer? And now we are asking questions, can it fix the printer, et cetera, right? And basically make the avatar do things that we may want humanoid to do. Of course, humanoid doesn't have the dexterity and so on and so forth. So, but we can show that it can be done conceptually. One of the key things that, a lot of the, even an individual component here, for example, when the person is going and showing, okay, this is the box, this is the container, this is something if the machine hasn't labeled it correctly, is to register the object with respect to the headset. So its 6 degree of freedom is registered with respect to the headset, and you move away from that, it still can be found, right? So conceptually, you can get back to it. We avoided use of SLAM and so on and so forth, which actually don't work that robustly well. And so yeah, we kind of put the human in the loop, made the human do a few things, and then we were able to get the exact position of the objects for the avatar to go and show things. So can the XR become a design canvas? So here we sort of wanted wanted to start thinking about, can it help in coaching for sports, but also in assembly, surgery, education, and so on and so forth, right? So imagine creating these immersive applications directly from natural language, just like you're creating an image with Gen AI today, right? So we wanted to create an entire workflow, entire application using language in a particular context, right? Show me how to make coffee, for example, right? Um, so if you so and we know that Gen AI in many cases is pretty good at breaking tasks down, and you can verify it and so on and so forth. So here's a very quick example
especially for non-experts. That's why we built Agent AR, a tool-augmented LM agent that designs and updates AR apps on the fly. With just a sentence like, "I want to learn how to make coffee," Agent AR plans, builds, and launches an interactive AR experience instantly. From guided examples to user-created ideas, Agent AR is changing how AR is made.
Yeah, what we did here was tricky, right? Like
creating AR
I'm just going to
applications.
jump this, but basically what we did was to show that it works. We just took all the previous papers that were nearby in the last 2 years, and we just did it with our agent AR. So pretty much we were able to create a lot of other applications on the back end. And key to this was a tool augmented agent. So that agent actually has capabilities in doing particular things. You give it that tool, and it can help you do that contextually. But you can see here, as you're doing the task, the backend actually is assembling the various objects and connecting them in ways by which the whole workflow for Agent AR can be authored. So I'm going to go past this, but basically this is a depiction of the workflow. So the backend layer captures the sensing, the perception, and the reasoning of the modules, such as object, the hand, the gaze tracking, etc. Right? Or you can think of it as a physical simulation. And the front end layer provides the rendering, the user interface, and the 3D assets. Right? So actually, at this time, a lot of our work in this area very closely was perhaps a year or two ahead of Google's current platform they just released. In fact, they have, they basically hired a bunch of our students into that team, but they have actually released one, and we are very closely associated with Android XR, which has some kind of an architecture that actually does this kind of stuff. So very current research, and a lot of the research gets attracted to applications and reality fairly quickly in this area. So sort of last piece, right, like the multimodality. I want to talk about action feedback and so on and so forth. So roughly speaking, right, think of it like industry in general and education, training, learning, doing things hands-on. Always need a lot of people to help people do hands-on. So we really can't scale that much. Working with machine tools and working with a lot of other physical things and training, either like semi-virtually or actually getting trained, right? Yet a lot of this knowledge is contained in flat computers and different manuals, and also people hold it the so-called tacit knowledge, knowledge that can't be encoded. So a lot of it exists, right? So how can we help bring that out? So get away from the one-on-one training, which has been the hallmark of how we always have learned, right? So a lot of the organizational insights can also come out. So multiple people are doing multiple things at different locations, such as maintaining, fixing, and so on and so forth. Can we connect all those pieces of knowledge, sort of like analogy, right? Is the work that was done for playing chess, for example, right? Like in 2024, and so on and so forth. So the idea is like, how can we do that? So we played in this area. We actually worked with a welding textbook writer, worked with a trailer truck company, and with a welding company to actually build such an application, right, for tailgate welding. And so the idea here was to incorporate what, one of the learning science ideas for reversing out from a goal. Can we reverse out all the individual constructs that go towards achieving that small piece of learning goal, and then slowly reconstruct backwards and assemble the whole application, right? So these idea of reversing the goals and personalizing the training, and of course, because it's immersive, user can engage and get feedback and so on and so forth. So we kind of put a lot of effort in our very first work. Of course, that piece now is more and more automated even in our own lab. So that was for welding. I'm sort of going to jump into more of physical space and design, right? You can say, right, like in a lot of these AR applications and so on and so forth, the physical feel is gone, right? Like, what am I doing, right? Like, I don't feel real, but I'm sort of holding this controller, etc. So we always, of course, used hands and physical objects in AR, but the question was, how can we develop smart tools which can act like a real tool, behave like a real tool, give you vibrotactile feedback like a real tool, and also it seems real because what you see, if it's realistic, it's real. It feels real, so it can become more real, right? So sort of making there's a virtual reality, but really not really virtual reality because you're actually handling something like a physical tool in VR. So this power tools, we call it Power VR tool, but basically we wanted one tool to multiply into all the other tools, right? Like a jigsaw, drill, a rivet, etc., riveting gun. So multiple tools. All of these give you different types of vibrotactile feedback. So we actually ended up working with an aerospace company, and this application is actually in test in there since the last 2 months inside the company. So very happy to get it to that level. It's been a lot of work actually. Last 3 years. Last 3 years, we have been working on it. We actually put the paper out after our application got into the company because of a lot of other issues in IP and so on and so forth. But basically, we learned the vibrotactile feedback by putting sensors on real machines, real people, different speeds, different materials, and so on and so forth. And then we built the design here with very new types of linear resonant actuators and so on and so forth, LMRs, which can give you a very high G-force, up to 10 or 20 G-forces, and they're fairly compact. Perhaps we couldn't have built this maybe 5, 6 years ago, right? They became compact, and we were able to design and build it in such a way that you get those the vibrotactile feedback. But also you can see there's a bunch of holes here for shifting weights. So the idea is by putting weights here, we get the inertial properties very close to the real tool. So you can actually get that. And then, like, of course, the vibrotactile feedback, then you have the position and so on and so forth. Then the idea was, okay, you want to replicate a drilling process, train in high precision drilling, and you can do that. We sort of mirror the drilling machine in the power tools, in our virtual physical power tool, and render the vibrotactile feedback there. Sort of like looking up a table in just a comparison to show that we are as realistic as possible in terms of the frequency and amplitude.
A POW VR tool capable of providing haptic feedback for power tools in terms of passive haptics. User.
Sorry.
POW VR tool capable of providing haptic feedback for power tools in terms of passive haptics. Users can add auxiliary weights to the weight linkage. While the ideal balance can be achieved by strategically positioning the auxiliary weights. And active haptics, which include the vibrotactile feedback associated with power tool operations. The active haptics or realistic vibrotactile feedback was achieved by the application of various actuators. In virtual reality, users can perform drilling operations while POW VR tool provide haptic feedback, and the simulator can provide verbal feedback to users based on how they performed.
Great job. Your angles and offsets are well within the acceptable range, showing careful control and precision. The depth is spot on too.
Yeah, of course, we showed a good case, but as you can see, we also aligned the language model to give you feedback like a real coach would. In fact, they were really happy with that feature. Fortunately, during all the testing times, it behaved very well. At least it's passed their initial tests. We do control the language feedback using constraints in the taxonomy and words and so on and so forth. We still don't have, I can't like write a paper in that area, but we got it working pretty well. So deconstructing and reconstructing physical AI, I kind of talked a little bit about it. And then like I'm going to sort of move to a little bit more of things that, more design oriented, right? So here, what we did was, and I'll move this into 3D pretty soon, embodied, but we kind of took and you can take any product and decompose it, of course, right? Like, and here this is a different decomposition. It's more like a visual decomposition using segment anything and break it into parts, and then we can analyze the parts with LLMs, do a lot of interesting things to create some kind of language knowledge graph around a bike, for example, here, right? So once you do that, we started using the handles in the text to change the design, like black, brown, mountain bike style, etc., because the handles now become our UI. And we kind of took a lot of things which were written and done in textbooks and design decompositions. There's tons of research done in this area in ASME, design theory, methodology, and so on and so forth. And we started using that to guide our interaction with the LLM, right? So color, style, texture, shape, structure, mechanics, material elements, all these become handles for you to change the design. And in doing so, we, for example, were able to convert designs into different things. So for example, in this case, a wooden chair to a very different kind of a chair. You can start using LLMs for ideation. We can generate a much, much bigger design space, attaching wheels and so on and so forth. So you can visualize the final design, but also you can convert it into 3D. Of course, it's a surface mesh model, but we kind of took it all the way using mesh-based diffusion ideas to fully reconstruct the 3D model and render it. Of course, now if you can break it into pieces and work with other types of geometric ideas, you could perhaps even machine it out of wood or make it out of wood, right? So this idea of coordination of language and speech also was interesting to us. So one of the questions we were asking here was, for example, in the previous one, you don't have a parameterized model. It's not controllable in pieces and so on and forth. And yet in CAD, we have designed things for ages using parameterization and features and so on and so forth. So can we use speech and gestures and break the speech, extract the function parameters, the object parameters, positions, etc., and timestamp it along with your gestures, coordinate the two again. And it turns out that, of course, we gesture so many things easily without knowing anything about any like CAD-like systems, right? So can we use a natural description that we can come up with to build 3D models? That was our question. And little bit of this, it's a fast video, but you can kind of see what's going on here. So he's just actually talking also during this time. I'm not, because we speeded up the video, but you can see his text. Like I want to create something in this form going from here to here. And I want the handle to start here and go around here. I want a spout to go here, et cetera, et cetera. And then immediately his parametric capability there appearing in the window, and he's modifying the design. So for example, this is one of the exercises in our CAD class, right? So we kind of showed that. That paper is just going to come out. So if you guys are interested, like I'll be writing general articles for common public on my LinkedIn. You can just send me a LinkedIn invite and you'll see more of this. If you don't want to read the whole paper, you'll see simpler versions of it. Here, of course, we also wanted to bring embodiment into sports. This is one of our lab's very active areas, is athletic AI, and sort of push the performance of AI systems in understanding where the ball is coming, its spin, its speed, where it's bouncing on the table, and have the capability to both coach humans, but also to take the human embodiment and what we know in how we play and bring those models alive into humanoids, right? So there's a lot of very interesting possibilities as a test bed. So we kind of embraced using sports as one of our test beds. I'm not going to get deep into the model here. Just this paper just got accepted in ICRA, but basically the idea here is think of the ball and think of the ball's position and height above the net. We, for example, use these as reward functions. We want the humanoid to hit the ball at a particular portion on the other side of the table with some height above the net, but also you want it to move into a position before it executes a stroke. So all of this has to happen in real time, right? After it sees the ball. So we created virtual simulator and gave the reward functions in the simulator for both the landing and the height, and also tracking of the paddle position and the ball position. We were doing all of this in simulation, and you can see here hundreds of humanoids sort of using reinforcement learning to build its capability to do this in real time. And then, of course, we have a real humanoid, which actually had fairly, it's playing at a fairly low level, but we're perhaps the first or the second team to actually show full body control locomotion for it to actually play with a fairly decent success rate. Of course, the ball is coming in the same or similar position. There's no backhand and so on and so forth. But nevertheless, that was an interesting demonstration. So I'm almost done. This is just things coming out of our lab. Agent Coach for helping people in physical training with language in real time. That's coming up. Am I Right is a take on using AI with handwriting, with matrices and equations and so on. It's the first demonstration of written AI, which math is written, right, not typed. So it's an AI LLM-powered AI tutor for math that's coming out in Kai. In ERify, we further push what you saw in Agent AR. It's agentification right from narrated videos to create augmented reality tutorials. And last is Just Shape. I showed you a snapshot of it, but a full detailed exposition of parametric modeling and how all those features are brought into languages are brought there. Couple of other things which will be very interesting to engineering and mechanical in general is a framework for articulated assembly motion prediction from huge numbers of gear-like assemblies that we train. We are working on mechanisms now, but basically that's it. So I want to kind of end by saying immersive reality will continue to fuse digital and physical worlds, both lived and shared. And the real world will become our interfaces, and we will not need any interfaces. We are the interfaces eventually, right? So and a little bit of add to the toy class that I started at Purdue. 30 students, now running 320 students. Lots of 3D printers, but they make all kinds of toys. Has been a fun class. It's now run by Min Liu, who's our lab's research scientist. So one of the very amazing toys that is one of my favorites there on the right. And thanks to all my students, and thanks to your team for having listened to me. I'm open to questions. Thank you so much, Farooq.
Thank you so much, Dr. Ramani. It was really interesting to me to see how we use AI not only in digital domains, also in physical world. Thank you so much. So now we open the question and answering session. Please feel free to raise your hand and ask your question to Dr. Ramani. Yes, go ahead, Zara.
Hello, thank you so much, first of all, for the very nice presentation. I'll surely go back to the presentation to understand it more better. But for now, my question is, like you mentioned, like using the denoising transformer that generates long coherent motion. So when generating a long motion sequence with diffusion model, how do you prevent drift or like physically unrealistic behavior over time? Is the coherence mostly learned from the data, or is there some structured constraint then that you apply? in
Yeah,
that model?
so the transition probability handling between different sequences, I think that was our main contribution in that paper. But in general, when you say drift, the the avatar itself doesn't drift, right? Like, so two or three things. One is the physical plausibility, legs have to be on the ground, etc. The hand holding the object is the area that we haven't solved. I think people are working on it currently. I just saw a very recent work done by in ICCV paper just come out, which has gone beyond what we have done. So motion, human motion, because plausibly, it's not a real human, right? It's an avatar. If it looks real, it feels real, it seems real, it's real. So it's pretty smooth in that sense. So it's in the Gaussian process itself removes the noise, right? So the denoising process removes the noise. So it seems real. We haven't transferred that to actual humanoid as we did in the table tennis case. But in the table tennis case, it's not using Gaussian process at all, right? So it's just reinforcement learning from the actual avatar. Yeah, so we don't know if the avatar motions and others that I showed in that area is actually transferable to a physical humanoid to see whether the humanoid will move smoothly, but the avatar seems to move pretty smoothly.
Thank you so much.
Thank you, Zareen. And Sarah, have you had a question?
Yes, I had a question, but thank you so much. It was really interesting presentation. It was really interesting. And one question that I have, in your system, in your XR design system, when AI generate or suggestion any kind of the instruction, how do you handle uncertainty or evaluate whether in this generated outcome is actually acceptable for decision making or not, just is visually realistic? How do you see this one? Or also, I think most of the design that you have at this time is based on the current situation, current things that you have. Do you see any way, for example, to integrate, just because I am working with predictive analytics, just I want to see, do you see any way to integrate predictive forecasting to your AI system that you are working to generate design account for future scenarios, not just current condition?
Yeah, really good question. So in all our studies, we have extensive human testing, right? In the computer-human interaction area, that's so all of them are IRB approved studies. Every one of them has at least 32 or more human subjects that, depending on the context, have tested the system, right? So that's partly might answer the first piece of the question. The second piece is of very current interest, and we have actually published papers in predicting motion. So there's InfoGCN++, which came out in PAMI, which I didn't present today, where we actually predict the future human motion ahead of time, right? So again, that can be very useful in many scenarios and settings before an error can happen, and that is of very current interest in the driverless car area and so on and so forth. So actually, that was collaborative work with Honda, but we didn't do it for cars. We did it for human motion. But also, it's very relevant question even for our table tennis. We as humans are trying to predict where the other human will be and where to strategize and give the other human a disadvantage, like put the ball in a position that they can't get to that place, right? Like, and also we are also trying to predict the spin and the speed and the location. We're doing all of this currently. Our approach to that is sort of the opposite of what computer vision and computer science people, most of them are doing. We are actually developing physics-based ball paddle contact models and aerodynamic based trajectory models, and taking surrogates of that and trying to see whether we can use it for coaching humans, number one, and number two, can we use it for coaching the humanoid, right? So to that end, the prediction either in the nonlinear FEA or others are guiding the decision making of the human or the humanoid. But InfoGCN++ will answer your other piece, right? Human motion prediction. There's continued work in that area. People are working there. It's sort of, we call it design intent, right? Like you're trying to do something, right? Can I complete the whole thing, right? Can I finish it before you start, right? Maybe not to that extent, but I think we were able to at about 20 to 30% of the segment of the actual motion beginning, we were able to complete the rest 60 to 70%. As the motion proceeds, the prediction confidence also increases. And it kind of hits fairly high level, 90 to 100%, even at, like I said, 30 to 35%, right? And we tested this across various action recognition scenarios. Yeah, so that was the extension of InfoGCN, which was the activity recognition work.
Thank you so much. Thank you. I look forward to read the paper that you mentioned. Thank you.
Okay, and the next is Dr. Naidu from Sleep Labs. Go ahead, Dr. Naidu.
Thank you, Karthik, for a very nice presentation and very comprehensive and lot of information to absorb. My question is about, we talk always about the large language models, right? But still, I think what is not heard much is large drawing or large design models. One challenge there is that normally designs are not available in public domain. You cannot Google a design because it's very proprietary to a particular company. So I was wondering whether there will be a day. What are your thoughts?
Very good question. It's an excellent question. So yeah, excellent question. In fact, a lot of my so excellent question. So we put out a fairly large data set, perhaps the second or third largest for CAD models. And like you said, they're all like at moderate level complexity of what is available publicly. The closest larger data sets are coming out of a company that PTC acquired, the guy who created SolidWorks. They are a little bit more open, and their model setting is also a little bit more open. Actually, the CTO didn't like their model being more open. He was complaining to me when I met him recently while I was at Boston. But it's called, it's PTC's acquisition. I'll give you the name very shortly, right? I lost the name. Oh, Onshape. Yeah. So Onshape. So a lot of the models we collected and others collected, and there's continuing effort in that area. So you're absolutely right. Real world, more complex models, the CAD designs of it are not available as is. But I think we are reaching a time where if you show me all the 1,000 components, I should probably be able to scan it and reverse parameterize it quickly, right? Even for a complex engine. So it's possible to do that, of course, but it'll take time, so people don't do it. Yeah, so I think, yeah, that's a very relevant question. I don't know. I don't think it is going to be answered in the physical world, but interestingly, if you take an image of even some of the moderate complexity parts, and if you put into Gemini, to my shock and surprise, it kind of does its own parameterization. It gives you some handles, and it's pretty decent to the level that, if they were parameterized, then I won't need to teach half of my class, right? One half before they start doing their own stuff. So yeah, but it's all of moderate complexity and not fully real world designs. That's a really good question. I think it'll chug along, and perhaps the CAD modeling idea itself has to be tamed as we go forward. But the precision, the complexity, and other things that existing workflows and software provide, it's hard for more disruptive approaches to break it yet. So they instead are starting to embed AI inside their systems, right, to do some of the things. So it's sort of, yeah, it'll be interesting to see how the future holds for complex designs.
Thank you. Great answer. Thanks.
Okay, thank you. If there is not any other question, we can end it up this webinar. And thanks again, Dr. Ramani. It was